Last week, we did the generalization of what is this process that we're going through, of what does the p-value mean, what does the critical regions mean, trying to decide, are we going to reject the null hypothesis or fail to reject the null hypothesis, kind of talked about how we do the wording on those. We even looked at what the test statistics are. This chapter is just bringing all of that together of let's do a test about a claim on a proportion. So we'll focus everything on proportion this time. On Wednesday, we'll focus on the mean when we know the standard deviation. Friday, we'll focus on the mean when we don't know the standard deviation. And next time, we'll focus on testing a claim about a standard deviation or a variance. So the process looks very similar to what we did on Chapter 7. As you guys noticed with Chapter 7, when it all came together in the test, you had to pay attention to which thing do I know and which one of the methods do I use. That's the big challenge on this test also. This test does not have very many problems. I don't remember how many I have on it. I have 2 or 3 just sort of general questions at the very beginning, and then I have about 4 or 5 questions for you guys to have to do. That it's just, you're going to go through the whole process of, I state what I'm wanting to be the claim and what my research has found, and you have to do the hypothesis test on it. And so you go through the whole process on several of these different problems. So going through the whole process is the main thing we're doing. When we're doing the testing a claim about a proportion, we'll be using the traditional method when we do it by hand. We'll do the p-value method when we use our calculator. Being familiar with the parts on each of these is important, because the few questions I have at the very beginning are really focusing in on some of the different parts that you need. When we get to section 8.6, which is testing the claim about a standard deviation or variance, we will not have a calculator method, so you'll have to do it by hand. So getting an idea of what it means with that traditional method is important, because on section 6 you have to do the traditional method, versus being able to use the p-value method when we're doing the calculator, and figuring out what you found is really the key pieces in here. Notation, n is still the number of trials. P hat is your sample proportion, which is the number of successes divided by the total number in that trial. P is our population proportion, which we use in our null hypothesis and has to be a piece of our null hypothesis. And Q is the proportion that's false, which is the 1 minus the P. Requirements for testing claims about a population proportion P. First, the sample observations are from a simple random sample. The conditions for a binomial distribution are satisfied. The conditions that n times p is greater than or equal to 5 and n times q is greater than or equal to 5 are both satisfied. So the binomial distribution of sample proportions can be approximated by a normal distribution, with the mean being the n times p, the number of successes, or number in our thing, times the proportion that you would expect to have as successes, and the standard deviation being the square root of npq. All of that goes back to our binomial distribution. So, recalling back in Chapter 5, when we talked about on section Part 2, the conditions for binomial distribution are satisfied, that was the fact that we had to have a fixed number of trials. The trials had to be independent, which meant the outcome of any individual trial doesn't affect the probability in the other trials. Each trial must have all outcomes classified into 2 categories. As usually we talk about success and failures. And the probability of a success remains the same in all of our trials. So those conditions still had to be satisfied. When we did that back in Chapter 5, we were able to find our mean being n times p and our standard deviation being the square root of npq. Now note, and this is the key piece in here, p is the assumed proportion, not our sample proportion. So when we are doing our trial, we will assume, from whatever the claim is, we'll make our null hypothesis that p equals some value. We will assume that to be true, and we will do the whole entire test assuming that we know p, which is the population proportion. If you know p was true, Then from our sample, once you know what the sample size was, we would expect the mean to be the sample size times the proportion of successes. We would expect to be able to find the standard deviation, the population standard deviation from those. We're assuming we know P is true, and we're working our way backwards through all of that. And so it's using what we talked about back in Chapter 5 and just kind of building on it. So our test statistic for testing a claim about the proportion is that Z is P hat, which is our sample proportion, minus P, which is our population proportion, divided by the square root of the quantity P cubed over N. Which, back in Chapter 7, in Chapter 7, we were doing the confidence intervals to find my margin of error. We took Z times the square root of that PQ over N. Well, if I'm trying to find my margin of error, that margin of error is the difference between the sample proportion and the population proportion. So solving this for Z instead of E, you would take E divided by that square root. Well, that's what this is E divided by that square root, where E is that margin of error, the difference between your sample proportion and your population proportion. So it's not a new formula, it's just rearranging an old formula when we're doing these. Now, it's in your reference sheet, and as I told you guys last time, you go from Chapter 7 to Chapter 9, but if you flip the page, Chapter 8 is at the top. So your test statistics are given to you up here at the top of that, where we last time fixed our chi-squared, which will be the one we look at in the, Section 6. So this is the test statistic we'll use when we do a proportion. Now, be careful again, I think I mentioned this last time, be careful between the p-value and the proportion p. P-value is the probability that that would happen, probability of getting a test statistic at least as extreme as the one representing our sample data. So that p-value is a probability versus p is a population proportion. So pay attention to what that notation means and be careful with that as it comes along. So if we look at page 406, page 406 walks us through how to find our, it walks us through our hypothesis testing. It's got both the p-value method and it's got the traditional method. The first steps are the same. So step 1 on both of them is identify the specific claim or hypothesis to be tested and put it in symbolic form. Step 2, give the symbolic form that must be true when the original claim is false. That way we can use those for step 3. Of the 2 symbolic expressions obtained so far, let the alternative hypothesis, H sub 1, be the one not containing inequality, so that H1 uses a symbol either greater than, less than, or not equal to. Let the null hypothesis, H naught, be the symbolic expression that the parameter equals the fixed value being considered. So then once we think we know what our proportion equals, that'll be the P that we assume to be the population proportion. Step 4, select the significance level alpha based on the seriousness of a type 1 error. Make alpha small if the consequences of rejecting a true null hypothesis are severe. The values of 0.05 and 0.01 are very common. Alpha will be given to you guys in any problems that you're doing. But if you were to be doing your own sample values, where you're doing your own calculations and your own research, you have to decide what that alpha means. Oh, and I didn't do the type 1 and type 2 errors. I'll do that at the end of class. Forgot we didn't get those done last time, so I didn't put them on the slide. Step 4 then, identify the test statistic that is relevant to this test and determine its sampling distribution. So when we are doing the p-value, because our test statistic was Z, we're looking at a normal distribution. So you'll be looking at your normal Z values as you're looking at doing things. Versus as we look at others, we'll do the student T distribution sometimes, we'll do the chi-squared distribution sometimes. And so try and decide which one of those we're using. That's based off whether we're doing a proportion, a mean with the standard deviation, a mean without the population standard deviation, or whether we're testing a standard deviation. So those first 5 steps are the exact same. Step 6 is when it breaks off, whether I'm doing the p-value method or whether I'm doing the traditional method. If I'm doing the traditional method, I will find the test statistic, which was my z-value, the critical values determined based on what alpha is, the critical region, so once we have those, is it a left-tailed, a right-tailed, or a two-tailed test to figure out the critical regions, draw the graph, include the test statistic, the critical value, and the critical region or regions. Then if I'm doing the traditional method, we will reject the null hypothesis if the test statistic is in the critical region. You will fail to reject it if the test statistic is not in the critical region. And then based upon whether we've rejected or failed to reject it, we will restate the previous decision in simple, non-technical terms and address the original claim. And that's based off using the wording that we had on that reference sheet. And so that'll be using one of these first 4 beginning parts and then using your claim at the end of it. Now we'll kind of step through the p-value method in just a little bit because I want to do a couple of problems with the traditional method first. So if we look at number 12 on page 421. Screening for marijuana usage. The company Drug Test Success provides a one-panel THC test for marijuana usage. Among 300 tested subjects, results from 27 subjects were wrong, either a false positive or a false negative. Use a 0.05 significance level to test the claim that less than 10% of the test subjects are wrong. Does the test appear to be good for most purposes? So, first of all, what is my claim? Okay, what's less than 10%? Okay, P, mu, or sigma? Okay, we're doing proportions right now, so that's P. If the claim is false, what would be true if this is false? Okay, P is greater than or equal to. So now when I go to write my null hypothesis, what would the null look like in this case? Okay, null is always equal. Which one of these is my alternative? Because your alternative is whichever one does not include the equals. Okay, so my one that doesn't include is just that less than. So my alternative in this case is the P is less than that 0.1. Your alternative hypothesis may be the same as the claim. It might not be the same as the claim. We're always testing the null hypothesis. So everything I'm doing is based off this assumption that the proportion is equal to 0.1. I'm going to assume now, since I'm making that claim, that I think it's actually less than 0.1, that less than 10% of the results are wrong. I'm going to assume, though, that it's equal to is the true statement, and I'm testing to see, with the results I got, what's the likelihood that the true proportion is 0.1, and my sample just happened to be what we had. So that is looking at the first, I think, 3 steps were just covered right there. Yes. So that's taking care of the first 3 steps. Now, in this problem, step 4, what is alpha? Okay, they give us alpha to be 0.05. Number 5, identify the statistic that is relevant to this test and determine its sampling distribution. And then, so in this case, if we're dealing with proportions, my sample statistic is going to be the z-score. And so now I need to find my test statistic. Now, I want to point out one other thing first. Notice all of this stuff happens before I find my test statistic. Honestly, all of this stuff should happen before you even do the research into what you're doing. You should not go out, take a sample, and then come back and figure out what you want to claim to be true. you should make a claim first, then go out and do the sample, and then come back and test whether or not it matched with what you already thought your hypothesis should have been before you went out and did the research. So you should already have, from some information you have before and just what you know, what is the hypothesis, what's my claim, and then you go out and you try to do get a sample to figure out if it really matches what you have or not. So in this case, we're trying to find the test statistic of z, which is p hat minus p over the square root of pq over n. What is p hat in this problem? Okay, it's going to be your 27 over 300. What is p? From my null hypothesis, I'm assuming I know p to be 0.1. So then p is the 0.1, q would be 0.9, and n was our 300. So go ahead and use your calculators and find what that value is. You can either do it in several steps or use parentheses correctly and do it all in one. Okay, so now that I know my z-score, so that is my test statistic, I also need to find my critical values and my critical region. So if I'm trying to find my critical values come from alpha. In this case, alpha is 0.05. Is this a left-tailed, a right-tailed, or a two-tailed test? That comes from my alternative hypothesis. So if my alternative hypothesis is less than, is that a one-tailed, a two-tailed, or is it a left, a right, or a two-tailed? Okay, it's pointing to the left. So this is it's a left-tailed test. So I'm going to put all of my alpha is going to go in this left-tailed test. So I'm putting 0.05 over here. What is the z-score that puts 5% to the left of that? No. From our tables. First of all, do I anticipate that this is a negative or a positive number? Okay, it's going to be negative because it's on the left side. So I'm wanting just to have that 5% being to the left, which is the one at the bottom of the negative 1.645. Because that's putting all 5% of it in that left tail. So that is my critical value. My critical value is the negative 1.645. My critical region is this region that we have shaded that is to the left of that negative 1.645. Now what I need to do is compare where is my test statistic in relation to my critical region. If my test statistic in this case was this negative 0.5774, which could just be rounded to negative 0.58, because when we're looking at those, we only go out to 2 decimals. If we find where that's at, so here is 0, negative 0.55 or negative 0.58 is about here. Is that in there that it's so far off that I have to reject the null hypothesis? Is it that extreme that's only in the lower 5%? No. This could happen by chance, could happen sometimes more than just 5% of the time. This could just randomly happen by chance. So is that a reject or a fail to reject? Fail to reject. It's not so extreme that I have to reject that this may actually have been true, that this was actually equal to 0.1. So this is a fail to reject. And I'm failing to reject that null hypothesis is true. So I'm failing to reject the fact that it might equal 0.1. So now I have to figure out what's that mean in just common sense terminology. So now I go back to using my words. Did my original claim include the equals? So my original claim was that P was less than 0.1. Did that include equal? P being less than 0.1 did not include the equal. Did I reject or fail to reject? So there is not sufficient sample evidence to support the claim that, and how did I word the claim? Support the claim that less than 10% of the one-panel THC results are wrong. So there is not sufficient evidence to support the claim that less than 10% of the test results are wrong. Now, questions about writing that part in there? And make sure that when you write that answer, this is like the conclusion. If you were in English and you were writing this big, long thesis statement and you had to make your final conclusion that needs to wrap up everything, this is that final conclusion that wraps up everything. Somebody should be able to read this statement and know exactly what you're talking about. It shouldn't be some sort of vague, saying something like there's not sufficient sample evidence to support the claim that, less than 10% is wrong. Well, less than 10% of what? Make sure it's going back that is less than 10% of, in this case, the one-panel THC tests are wrong. Now, for the other part of this is, does this test appear to be good for most purposes? So if I just came to the conclusion that there is not sufficient sample evidence to support the claim that less than 10% of the results are wrong, does this sound good or not good? Not good. Okay? This is saying it can't support the claim that we're wrong less than 10% of the time, which is kind of going with that means that if it can't support that it is wrong, that it could possibly be wrong more than 10% of the time. And if my job depended on the fact that it came back, my drugs by not taking marijuana, that my job's depending on this line, I want it to be right more than just 10% of the time, or not wrong less than 10% of the time. And so I want something a little bit more accurate than what they were talking about here. Questions on that one? So it's wrong too often to be really considered reliable in this case. Now, if we go through, so this was going through the traditional method. Traditional methods used if I don't have a calculator that's going to be able to do a lot of the work for me to calculate out the p-value. I'm on the wrong page still, sorry. Finding this critical value, we use 95% so often. If it's a one-tailed test, then my critical values are either going to be the negative 1.645 or the positive 1.645. If it's a two-tailed, it's about 1.96 and the negative 1.96. We use those numbers so often that if it's a z-score and we're doing 95%, if you're doing this very often, you pretty much have those numbers memorized. They're easy to find in the table. The p-value method is much easier to use if you're using the calculator. It's going to find the probability for you. And so when you're doing the p-value method, actually let's walk through it with the steps, because I guess I didn't talk to you about them. If we look back at page 406 again, those first 5 steps were identical to each other. Step 6 with the p-value method changes. Here you find the test statistic and you find the p-value when you're doing this, which is the probability that we get something that extreme or more extreme. Draw a graph and show the test statistics and the p-value. Then for step 7, you'll reject the null hypothesis if the p-value is less than or equal to the significance level alpha. You will fail to reject the null hypothesis if the p-value is greater than alpha. And then step 8, still same, restate this previous decision in simple, non-technical terms and address the original claim. So when I'm finding my p-value method, I'm finding the probability that I get something that extreme or more extreme. So the part that changes, and actually I'm just going to squeeze it into the same slide. The part that changes when I'm doing the p-value, I still have to find my test statistic. So I still have to do this step, where I have to find out what z is. Once I know my test statistic that z is the 0.58, let's see, we do it this way. This piece here was doing the traditional method. If I'm doing the p-value method, I still draw myself the diagram. The difference is now if I'm doing the p-value method, I take my test statistic and I figure out the probability that I can get that value. So my test statistic in this case is the negative 0.58. Now, to find my p-value, it does change whether it's a one-tailed, a two-tailed, left-tailed, right-tailed, or two-tailed test. And that was up here at the top. So we have our wording down below. We have above it how to find your p-value. First question, what type of test is this? Am I dealing with a left-tailed, a two-tailed, or a right-tailed test? Okay, I'm doing my left-tailed. My p-value then is the area to the left of that test statistic. If I was doing a two-tailed test, that's when you had to double the area. But if I'm just doing a left-tailed, I want to know what's the probability that I can get that extreme or to the left of that. So if I'm trying to figure out then, what's the probability that I can get the 0.58 or any value to the left of this? That's going to give me my p-value. Well, the probability that I have a z-score that's less than negative 0.58 means I'm looking at my table. So I'm back to looking at my z-scores on my table, and we're doing the negative z-scores. Because it's a z-score, we're looking across down this left column to get to the negative 0.5. Our 8 is across 0.08 is across the top, and we get 0.2810. Everybody remember reading your z tables, okay? So we're getting our probability that the area to the left is 0.2810, and the area to the left is what I wanted this time. So that's my probability. So my p-value is 0.2810. The probability that I can get my test value, my sample values to be this extreme or less is going to happen about 28% of the time. Is that a reject or fail to reject? So now I compare that to alpha. My alpha was the 0.05. Is that higher or lower than alpha? It's higher. If my p is high, if my p-value is high, do I reject or fail to reject? Fail to reject. If the P is low, the null must go. If the P is high, the null will fly. So this is a fail to reject. I will come to the same conclusion as we came to before. And so now we're going to be back to the fact that we will fail to reject the null hypothesis. So I'm failing to reject the fact that it might equal 0.1. And you'll come to the same final conclusion because now we're still saying the fail to reject. And so my wording is going to be the exact same wording that we did before. When we go back to the fact that did my claim include equals was no, we failed to reject. So there is not sufficient sample evidence to support the claim that the test is wrong less than 10% of the time. Yes. Now, the reason I said that if we're doing it by hand, the p-value is more of a pain, is because this changes, your z-score is your test statistic changes every time you change anything within the problem. Your test statistic is going to change. If I change what I have as my claim, I've just changed my test statistic. If I add one more person to my sample, then everything has changed. And so all of that will change each time, versus if I did it by hand, my critical value, my critical region would stay consistent in those cases. And so it's a little easier to find those by hand. But the calculator will give us the p-value when we do those. Keep in mind, though, the calculator is only going to work for the first few methods, and it won't work with our chi-squared distribution. So you'll have to be able to do the traditional method when we get to that last thing. So if I'm doing the calculator method, if we go into stats, arrow over to tests, we are going to do the fifth one down, sorry. The fifth one down, which is the one proportion z test. So this is different than doing the interval. I'm not trying to find my confidence interval. I am testing a hypothesis, and I'm using my z-score to test my hypothesis. P naught is what we stated to be true. It comes from your null hypothesis. That's why it's got the little 0 on there. I'm stating that P is equal to 0.1, and so you'll put in that 0.1. X is the number of successes that you had, which was 27. N is the number of my sample, which was 300. Then it's asking what kind of test am I doing? Is my proportion not equal to, less than, or greater than? Well, we're testing that it's less than, so you hit that middle one. And then you would do calculate. So you're putting in your null hypothesis, the sample that's true, or what you had as your number of successes out of the total number in our sample. In this case, we tested less than, and we'll calculate that out. And it's telling me my p-value. So now it tells me a lot of stuff in this. First of all, it's telling you what my z-score is. That is my test statistic. That is the same value we had a little bit ago when we did the calculations, that negative 0.577. So we rounded it to negative 0.58. Tells me my p-value, which the p-value is that probability is 0.28, which when we did it, we got the same number. We got 0.2810 versus 0.2819 that they had. Then we get the p-hat. P-hat is your sample proportion. In our sample, we had 0.09 was the number of the proportion that was wrong, out of my sample size being 300. So be careful as you're reading it that you recognize P stands for p-value, p-hat stands for the sample proportion. One of the big problems I see is you guys sometimes write the wrong values for your p-value with having that p showing up in there. Sometimes p-hat is already given to you directly. If I already give you what the sample proportion is, that makes it more challenging to be able to figure out what to put in there. So if I'm trying to use my calculator and I don't know the p-hat, or I know p-hat, but I don't know what the number of x's are, sometimes I have to calculate those out. So 10% of the observed sports cars are red. So p-hat is the 0.1. Sometimes you have to so sometimes I give you p-hat, sometimes you have to calculate it. 98 surveyed households have cable TV and 54 do not. So how would I find out the sample proportion of the amount that have cable TV? It is not 54 divided by 96. So how would I find out the proportion that do have TV or do have cable TV? And 96 out of the total, which is, we'd add the 96 and the 54 together to get 150. Okay, so the 96 out of the total of 150 would give you that 64% of them had cable TV. Okay, questions on there? I do want to go back and look at the two types of errors, but I'll let you write down the assignment first. Don't forget you can start registering for classes. Also, don't forget to do your course evaluations. Again, the course evaluations are anonymous. We won't know who did them, so you can say whatever you think's accurate. Also, our test is going to be on April 15th, so I think that's Friday next week. Is when our test should fall. Is it next Wednesday? Okay. So our test falls next Wednesday is my plan. Okay, the types of errors. This is what we ran out of time on last time. I will not ask you to do the types of errors, but I do want to mention those to you. First of all, a type 1 error. Oh, and I also need to talk to you about your grades. A type 1 error is the mistake of rejecting the null hypothesis when it's actually true. That's what alpha is talking about. So when I'm talking about alpha being 5%, it's saying 5% of the time I'm accepting the fact that I will be wrong about 5% of the time. That I've rejected that null hypothesis when it really was a true one. So we're saying the probability that it's actually going to occur, given that we know the null hypothesis or accept the null hypothesis to be true, what is that probability that's going to be out that extreme? If I'm doing a one-tailed test, I'm saying 5% on that left tail. Well, it might actually happen that we have a sample that's way extreme, way lower than what the true proportion of the population would be. That alpha, that's telling me the mistake of rejecting that null hypothesis when it was actually true. The type 2 error, which we won't use at all this semester, is beta. The type 2 error is the mistake of failing to reject the null hypothesis when it's actually false. And so looking at both of those two things come in on a lot of different places. So we hope to be in these correct decisions where we decide to reject the null hypothesis because it really was wrong, or that we fail to reject the null hypothesis when it was actually true. Those are our goals. But we have the possibility of those errors. The type 1 error is that we decide to reject the null hypothesis when it really was true. The type 2 error is that we fail to reject the null hypothesis when it was really wrong. And so those kinds of errors are things that we try to avoid, and calculating out alpha and beta and accepting how far off are we allowing ourselves to be falls into statistics a lot. Okay, grades. I have updated grades. You should have, what tests have we had so far? We've had the chapter 1, 2, 3, chapter 4, 5, chapter 6, chapter 7. So we've had 4 tests. We have 6. So you've taken 4 tests so far, so that's a total of 400 points. You have your homework average, which will be worth 100 points. You have your project average, which is going to be worth 100 points. I have updated all of those as of 30 minutes before class started. And so we've got so far a total of 600 points that we have done. Granted, homework and projects can still change a little bit because we'll still be doing some more of those. We still have left the chapter 8 test and the chapter 10-11 test, which are both worth 100 points. And we have left the final, which is going to be worth a total, wrong number. The final, which is really worth 200 points. We will have a total in here of 1,000 points when we're done with the semester. So we've done about 600 points out of the 1,000 points that we have in there to do. if you wanted to figure out what you have to do to get your grade to what you're wanting, if you're wanting an A, it's so easy in this class. 90% of the 1,000 means to get an A, you need at least 900 points. To get a B, you need at least 800 points. To get a C, you need at least 700 points. To get a D, you need at least 600 points. So you can look online and figure out from all of your projects, your homework, your 4 tests, take each of those scores, your homework and your project. Take each of those, figure out how many points you have right now out of the 600. So if you had 100% on everything right now, you could have a D guaranteed, which nobody has. But if you did, that would be a possibility at this point. Then take how many points you have out of the 600, subtract it from what your goal is. So if you're aiming for an A, 900 minus however many points you have left, or you already have had, tells you how many more points you need to get out of the 400 that are left to work with. So you can figure out what grade you need to get on the next 2 tests and on the final, assuming you keep your homework and project average at or above where you currently are. Then that would tell you how to figure out your grades.